Welcome to the presentation on toll and toll carbonization, part 1 of the basics. Toll is a complex mixture of organic compounds, the principal elements of which are carbon and hydrogen, with smaller amounts of oxygen, nitrogen and sulfur. It also contains ash, which consists of non-combustible components mainly made up of inorganic compounds. Tolls are of two types: non-protein or steam tolls and protein orbital tolls. Protein tolls are suitable for carbonizing and have special characteristics. Protein tolls are classified on the basis of their protein properties. They are fine protein toll, medium protein toll, semi or low protein toll. Carbonization of toll, also known as toll, is done to produce toll. It is destructive distillation or thermodecomposition of protein toll. It is done either in absence of air or in the presence of controlled quantity of air to produce a carbonaceous residue known as toll. Protein tolls are important raw material in the production of toll since they decide the toll properties. They may have low, medium or high volatile matter. Protein tolls are defined as those tolls that on carbonization pass through softening, swelling and resolidification to produce toll. Required toll properties are uniform size, two distant CRI, CSR and Mitham values, porosity with minimum volatile matters and minimum ash, throat-in temperature, throat rate, throat-in time, quenching practice and throat handling during toll carbonization process affects throat quality. Modern throat making practice involves carbonization of a blend of two or more of protein tolls. Protein toll blends may consist of different tolls ranging in quality from tolls with very high protein properties to tolls with almost zero protein properties. Blending is needed to control the properties of the resulting toll, to optimize the quality and quantity of byproducts, and to avoid the expansion shown by certain types of toll that may cause excessive pressure on the wall walls during the protein processing. Some of the properties of protein tolls affecting quality of throat are particle size, bulk density, total moisture and margin of toll. Other important properties of protein tolls needed to produce throat qualities are throat protein and taking properties such as fluidity, dilatation and crucible swelling number, rate-in value, etc. Appropriate and indicated by the reflectance value MMR. Vitrinate and vitrinate distribution V9 to V14. Besides protein properties, other important properties of toll include moisture, ash, sulfur, phosphorus and alkali percentages and ash fusion temperature. Low temperature, ash, sulfur and phosphorus content in the toll are desirable for production of good quality toll. Quality requirement of protein tolls: total moisture. High moisture creates handling problem and lowers available carbon. Ash, high ash content reduces PF productivity and increases throat rate in the furnace. Volatile matter, high volatile matter reduces the yield of throat but improves the throat gas generation. Sulfur, high sulfur increases the sulfur level of hot metal. Phosphorus, close to the hot metal, creating difficulties in desulfurization during the steel making. Crucible swelling number, prime protein values. Tolls have high CSN values while soft protein tolls have low CSN values. Maximum dilatation, its value in toll blend depends on the value of maximum dilatation in the toll blend components. Maximum fluidity, higher fluidity gives better friability in the throat domains. Alkalis, high alkali content in the is not desirable in blast furnace and also affects the blast furnace lining adversely. Ash fusion temperature, AFT in protein tolls is to be higher than the maximum protein temperature. Rate-in throat type, the value of rate-in is to be G5 minimum in protein tolls. For soft protein toll, the limit of rate-in value is G minimum. Mean maximum reflectance, the value of MMR in protein tolls vary in the range of 0.85% to 1.35%. Soft protein tolls have lower MMR while hard protein tolls have higher MMR. Vitrinate, the value of vitrinate in totenthal is 50% minimum. For soft totenthols, the limit is 45%. Vitrinate distribution V9 to V14, the value of vitrinate distribution in totenthal is 70% minimum. Toll carbonization can be carried out at the following three temperature ranges. Low temperature carbonization is carried out in the temperature range of 500 to 700 degrees centigrade. In this type of carbonization, the yields of liquid products are higher, while that of gaseous products is low. The tote produced has higher volatile matter and is free burning. Medium temperature carbonization is done at temperature range of around 800 degrees centigrade. This carbonization produces smokeless soft tote. Byproducts produced are similar in characteristics to high temperature carbonization. It is rarely practiced these days. High temperature carbonization is carried out at a temperature which is above 900 degrees centigrade. The carbonization gives high yield of gaseous products and low yield of liquid products. This type of carbonization produces hard tote and is normally done to produce metallized tote from totenthols. Carbonization process, toll to tote transformation, takes place as the toll is heated. When the state of fusion is reached, the layer of heated toll softens and fuses. From about 375 to 475 degrees centigrade, toll decomposes to form plastic layer. Destructive distillation reactions proceed rapidly in the plastic layer with evolution of volatile products. At about 475 to 600 degrees centigrade, there is a marked evolution of tar and aromatic hydrocarbons compounds. Gas and condensable vapor are entrapped in the plastic mass, and as they expand, tend to swell it. As the reaction proceeds and the temperature of the fused zone increases, plasticity of the toll decreases. With continued heating and evolution of gas, the fused layer gradually resolidifies into semi-tote, having typical cellular tote structure. Tote is at this stage still contains substantial volatile matter. As the temperature increases further beyond 600 degrees centigrade, the destructive distillation reaction continues with the evolution of gas and liquid tar. Tote stabilization takes place as the temperature increases from 600 to 1100 degrees centigrade. This is characterized by contraction of tote mass, structural development of tote, and final hydrogen evolution. At this stage, the final reaction takes place. These reactions split off hydrogen from extremely complex, high molecular weight hydrocarbons. With increasing temperature, the tote mass shrinks with the development of synthetic attacks. The figure shows typical toll carbonization. This is the toll preparation section, this is the carbonization section, and this is the tote handling section. During the carbonization of totenthal, around 25 to 30% of toll charge is given off as effluent gases rich in volatile matter and moisture. This gas is known as tote oven gas. In the non-recovery or heat recovery tote ovens, the gas is burned in the oven itself and provides the required heat for carbonization of tote. In case of byproduct battery, the evolved gas is removed as raw gas and is treated at a byproduct plant. In a byproduct plant to give a clean pure gas. In the byproduct plant, condensable, corrosive and economically valuable components are recovered. During the cycle of toting, the gas is produced during majority of toting period. The composition and rate of evolution of CO gas changes during the period, and the evolution of tote oven gas is normally complete by the time the total charge in the battery reaches 700 degrees centigrade. The clean tote oven gas after treatment in the byproduct plant contains water vapor, hydrogen, methane, nitrogen, carbon monoxide, carbon dioxide and hydrocarbons. Saturated gas from the tote oven battery contains around 46% to 48% water vapor. Other components of gas contains hydrogen, methane, nitrogen, carbon monoxide, carbon dioxide, high paraffins and unsaturated hydrocarbons like ethane, ethylene, etc. And oxygen etc. Raw total gas also contains various contaminants which give total gas its unique characteristics. These consist of tar components, tar acid gases, tar base gases, benzene, toluene, gyrene, BTX, fraction, light oil and other aromatics, naphthalene, ammonia gas, hydrogen sulfide gas, hydrogen cyanide gas, ammonium chloride and carbon dioxide. This gives a block diagram of the treatment of total gas. Taking mechanism. When the total are carbonized, then first the plastic mass of the optical isotopic is formed and thereafter gradually laminar pneumatic liquid crystals are formed. These polymer phase is called mesophase. This is the intermediate phase between the isotopic fluid toll and the solid anisotropic semi-toll ultimately formed from the mesophase and has properties which are intermediate between solids and liquids. If the fluidity of the intermediate phase is quite high, then mesophase tolls immediately into a single larger unit. Over a range of increasing temperature, mesophase form continuously grows in size and ultimately touches each other. Thus, the mesophase can solidify and convert from protein toll into the optical anisotropic structure of the toll. Toll handling and preparation is an important activity to prepare toll blend suitable for carbonization. Various steps of toll preparation for the protein include reception, unloading and storage of toll, preliminary crushing, storing, proportioning and blending of toll of different grades, toll making, waste addition to the toll blend, final crushing, mixing and transportation of toll blend to the toll tower. Toll needs to be stored at various stages of the preparation process and conveyed along the toll preparation section. Crushing and steaming are the important part of the toll handling and preparation plant. Crushing reduces the overall size of the toll so that it can be more easily processed and handled. Steams are used to raise the size of toll. Steams can be static or mechanically vibrated. Selection of proper toll blend is always a big challenge for toll producers since the blend has to meet following requirements. It has to meet the requirements of crushing during toll preparation. All the components of toll are neither to be over-crushed or under-crushed. The size toll blend for charging the toll is to meet the requirements of density, flow and the size fraction. It is to have necessary protein and taking properties for producing toll of quality, which means the quality requirements of BF toll. Three basic quality requirements of BF toll are to provide heat for endothermal reaction taking place in BF, to act as a reducing agent by producing the necessary reduction gases, and to provide a permeable support in the BF for the iron bearing burden. It is to provide safe pushing performance in the total. It must not put excessive pressure on total walls during the process of torquing and damage them. It should meet the yield requirements not only of BF toll but also of total gas. A proper toll blend does not produce excessive net torque and torque freeze. Finally, it is to be economical. In view of the varied types of requirements, the decisions regarding toll blend are not taken on an ad hoc basis, but after careful considerations. Toll blend need to be designed so that balance can be achieved between the competing sets of requirements such as throughput, high quality and cost efficiency, etc., while keeping importance of battery life in mind. Toll blend design efforts are required to be focused on to satisfy both physical properties, to satisfy both technical properties, to satisfy both pushing performance, to satisfy maximum usage of low value carbon materials, soft tolls, to meet the economical requirements and to be assured of continuous availability of toll fractions to avoid frequent blend changes. Toll is usually received in railway wagons. Toll conveyor belts transfer the toll as needed from Cold storage pile to mixing bins where the various types of toll are stored. Toll is then transferred from the mixing bin through a crusher where it is pulverized to a size of minus 3.2 millimeter, 85% minimum. The desired size depends on the responsibility of toll to toting reactions and the ultimate desired tot strength. Low volatile tot more readily if particle size is small, and smaller particles are reported to increase tot strength. The pulverized toll is mixed and blended, and sometimes water and oil are added to control the bulk density of the mixture. The blended toll mixture is transported to the toll tower storage bunker on the top of the toll. The charging method in case of top charging is normally by gravity with toll charging car. In case of stamp charging, the stamp toll tape is charged from the oven side door. The special techniques of toll blend preparation for toting toll include selective pressing of tolls, making use of pneumatic separation, thermal treatment, preheating of toll blend before toting, partial briquetting of toll blend, and toll blend preparation for stamping. There are three proven processes for carbonization of tolls. The type of tot ovens used in these three processes are beehive tot ovens. They are a non-recovery tot ovens, byproduct tot ovens, heat or energy recovery tot ovens. In these ovens, heat energy or of flue gases is recovered in the form of steam. Tot ovens are usually built in rows, one oven besides another. Such a row of ovens is termed as a battery. A battery usually consists of many ovens, sometimes hundreds in a row. In non-recovery and heat recovery ovens, there are common walls between neighboring ovens, where in byproduct ovens there is a common heating flue between the adjacent oven. A beehive oven is a simple fabric chamber built with an arch roof so that the shape inside is that of an old-fashioned beehive. Its dimensions are typical 4 meter in width and 2.5 meter in height. Rail tracks for handling the toll to the ovens ran around the top, and other rail tracks for the handling of tot cars ran besides the oven. The roof has a hole for charging the toll from the top. The discharging hole is provided in the circumference of the lower part of the wall. Toll is charged into an empty oven through the hole at the apex of the dome. It forms a cone-shaped pile which is leveled to a uniform layer by means of a rake passed through the door to produce an even layer of about 600 to 900 mm deep. Beehive tot ovens are now obsolete, an obsolete process because of its small capacity and the very large amount of pollution it produces. However, it is still being used. Typical beehive oven is shown here. This is the toll bed, this is the height, this is the width, and air supply, zone of combustion, and this is the refractive diamond. Toll in byproduct tot ovens is carbonized in the excess of air, and these ovens are operated with positive pressure. Tot making pressure process in these tot ovens is called byproduct tot making. Hence the off gas is collected and sent to the byproduct plant where various byproducts are recovered. Tot ovens are the chambers made of refractories. A battery consists of 20 to 100 adjacent ovens with common side walls made of high quality silica and other types of refractory bits. Typically, the individual tot ovens are 11 to 18.74 meter long, 0.35 to 0.5 meter wide, and 3 to 7.4 meter high. The wall separating adjacent ovens as well as end wall is made up of a series of heating flues. The majority of byproduct batteries have multiple flues, but a few batteries of very old type have horizontal flues. At the end of the toting cycle, doors are and both ends of the oven are removed, and when the tot is pushed from the oven by a ram that is extended from the pusher machine, the tot is pushed through a tot drive into a quenching car. This is the tot-on battery, this is the charging car, this is the pusher, and these are the fuse and this is the French dry. In heat recovery ovens, volatiles involved during toll carbonization are not recovered as byproducts but are combusted in the oven itself in the presence of controlled quantity of air. The heat of the volatiles of involving gases is utilized for protein of the toll mass into toll, and thus no external heating is required. The higher level of heat potentially is used to break up the potentially polluting hydrocarbons into constituent combustible compounds and to burn them, thus avoiding the potentially hazardous pollution. The heat constant to combustion is only partially utilized during the process, and the balance heat in the waste flue gas is recovered for energy generation. Heat recovery ovens are horizontal design and operate under negative pressure. These are the typical heat recovery ovens. The cross section is shown. Here the two ovens are shown. Here the toll is being pushed, and this is the flue gas coming out of it. This is the comparison between heat transfer of a heat recovery ovens and the byproduct oven. This is the byproduct oven. These are the heating walls, and heat transfer takes place horizontally by in the non-recovery oven. Burning takes place on the top, and heat travels from top to bottom in DI ovens. And in heat recovery oven, since the hot gases goes below, heat is also transferred from below and from the top, and both sides the heat transfer takes place. Thank you for attending the presentation of the toll and toll carbonization basics part 1.